CPU Technology Overview. 1. Introduction. The Central Processing Unit, CPU, is the primary component of a computer that performs most processing. Dubbed the brain of a computer, the CPU interprets instructions from a program and executes them. 2. Historical evolution. Vacuum tubes. Early computers like the ENIAC used vacuum tubes. They were large, consumed a lot of power, and were prone to failures. Transistors. The invention of the transistor in the late 1940s marked the beginning of the microelectronics revolution. Transistors were smaller, faster, and more reliable than vacuum tubes. Integrated circuits. By the 1960s, engineers were embedding multiple transistors on silicon chips, paving the way for microprocessors. Microprocessors. The Intel 4004, released in 1971, was among the first commercially available microprocessors. It marked a significant leap in processing capability. 3. CPU architecture. Von Neumann architecture proposes a system where the CPU, memory, and I/O devices are interconnected. Most computers today still use a variant of this architecture. Harvard architecture proposes separate storage and signal pathways for instructions and data, allowing data transfers to be simultaneously performed. RISC versus CISC. 1. CISC, Complex Instruction Set Computer, CPUs designed with a full set of instructions. 1. Examples include the Intel x86 architecture. 2. RISC, Reduced Instruction Set Computer, simplifies the processor by efficiently implementing only the instructions that are frequently used in programs. 2. Examples include ARM processors. 4. CPU components. 1. ALU, Arithmetic Logic Unit, executes arithmetic and logic operations. 2. Registers. Small storage areas that hold data, instructions, or addresses. 3. Cache. A small-sized type of volatile computer memory that provides high-speed data access to the processor. 4. Control unit. Manages various components of the computer. 5. Multi-core processors. Modern CPUs often have multiple cores, which are essentially multiple CPUs in one. This enables parallel processing, where different tasks are handled by different cores. 6. Clock speed and overclocking. The clock speed of a CPU determines how many cycles it can execute per second, measured in GHz. Overclocking is the practice of increasing the clock rate of a CPU beyond the rate at which it was originally designed to run. 7. Hyperthreading. A technology introduced by Intel where a single microprocessor appears as two separate processors to the OS, allowing for more efficient use of resources. 8. Modern CPU developments. 1. Quantum computing represents the next frontier in computation, leveraging the principles of quantum mechanics. 2. Neuromorphic computing involves designing chips that operate more like the human brain. 9. CPU manufacturing and brands. While Intel and AMD are the dominant players in the personal computer space, other companies like ARM, Qualcomm, and Apple, with its M1 chip, are significant in the mobile and low-power device sectors. 10. Cooling and power consumption. As CPUs become more powerful, they generate more heat, requiring advanced cooling solutions. Power consumption and thermal output have become major factors in CPU design. 11. Future of CPUs. While Moore's law has been the guiding principle for CPU development, doubling transistors roughly every 2 years, physical limitations of silicon are posing challenges. New materials, architectures, and computing paradigms are being explored to continue the trend of exponential growth in computing power. Conclusion. The CPU remains a marvel of modern engineering, evolving continually to meet the demands of modern software and applications. As we transition into a more digitally interconnected era, the demands on processing power will only grow, ensuring the CPU remains at the forefront of technological advancements.